And we are recording. Good. So that's perfect. Dan, do you mind sitting over here next to me?
I'll just give you this.
Oh, you are?
Okay. Yeah. A lot.
Then I'm going to keep that.
You need to log into your email or
no, we can just connect via the regular Zoom link.
Okay, so I need to connect.
Yeah. Or I could just log on to Zoom here with your. I could just log on with my account to Zoom.
Okay, yeah, that
works. They're over on the other side of the building, in the ocean engineering section. Straight through the high bay, and then make a right.
like the IOB.
I can't do. Hold on.
Right, so there's your online.
Okay, great. I'll do that then. Thank you so much. I can't. I'm like, oh.
No more classes.
I know. Like so many times.
So what did you go with the second one? Taking notes?
3 weeks. Yeah, I also 4 cities. I had a lot of work stuff.
Maybe she's in the chat. You didn't chat on that side?
Oh.
I try. I mean, I listen all the time. Yeah. Unless someone's really talking to me or you know, maybe all the time. Unless
Well, I can't do it from my account. I have to go into the. Can you bring the Zoom link up on here? I can't do it from my account, or it kicks me off of this one.
So you want to log into the Zoom?
Yeah.
See.
Let me move this one out of the way. There we go. So we're recording.
The quick keys or muties. I don't know if we want to do the first one or not. Just hit that. Yeah, that's to the mic.
35
And the sound. Just hit that.
I'm sorry, 0.
I keep it on.
Yeah, this one we've done.
Alright.
Your way.
I mean, it looks like me, but.
That's
I'd like
okay.
to get out of that. So you can. We're just working inside of a Word document.
Tomorrow.
Really?
Yes, nope, I'm gonna turn it
Well,
over here. I just need to listen to the chat room. There we go.
Okay.
Thank you so much.
Do what you need, everything you need now? Or?
Yes, thank you.
They're too big. Or maybe they just have to. Yeah.
Okay.
I used to use because I was very.
There we go. All right, can everybody hear me? Hopefully, this is Jen. Can people hear me online?
Yes.
Awesome. And good. So it's 12, and I figured probably a good time to start. I'm going to give a few intro slides. So speaking right now is Jen Mixes-Olds from the University of New Hampshire. And we are kicking off today with the 2018 seminar series for the spring term. And our speakers today are going to be Holger Klinck from Cornell and Chris Whitt from JASCO. Chris, I might have to apologize. I might missed a title, but I didn't know what your title was. So if I have missed a title, I apologize right up front. Chris is going to be talking first about underwater technology, and Holger is going to talk second about terrestrial technology. The next seminar series, the next seminar in the series is on February 13th. It's going to be animal density estimation from acoustic data. And we're going to have a split session again, active underwater acoustic data. Dr. Mike Jeck is going to be talking about, and passive acoustic data is going to be Dr. Danielle Harris from the University of St. Andrews. So that'll be next month. And then in March, we are going to wanted to at least highlight this webpage. This is our working group webpage, which is where you go to register for the March 20th Northeast Regional Environmental Acoustics Symposium. You'll find there a registration form and part of that registration is to submit an abstract. We're asking and encouraging all students and faculty to submit research abstracts, and you can do that there. We're also encouraging anybody who is part of an acoustics program at their university and would like to advertise their acoustics program for their university to make a poster for that and bring that, and we will put that in a special section of the poster so people can, students can look at potential programs in the area. This is coming right off the heels of the last ASA where there was a special poster session for acoustics programs. So I know, for example, UNH already has one. I believe URI already has one. So bring those posters, you reuse them, again, make a new one, however you'd like, but please bring information on your university's acoustics program and offerings.
The registration page is under the activities tab.
Okay, the registration page is under the activities tab, so that's where you can find that. Two other things I wanted to highlight that I'm aware of in the region coming up this summer with application due dates coming up soon. There's a marine acoustic sonar systems and signal processing short course here at UNH, June 18th to the 22nd. And this is the website for that. Second opportunity and this is open to anybody, industry, federal government, local government, students. This is open to everybody. And then CBAS 2018, this is a marine bioacoustics summer school. This is only open to enrolled graduate students at their university. So this is a graduate student course. It's a week, very intensive, focused on marine bioacoustics during the summer. It'll be from July 8th to the 13th this year. And the registration site is open at this web address. So people who are interested in that, just make sure, we always get applications every year of people who are not enrolled graduate students. You don't meet the eligibility criteria, which is again listed on here. Whoa, okay. So just know that. There, I am done with the intro slides. So I'm gonna stop sharing right now. I've stopped sharing. Chris, if you hit the screen share on yours, you should be able to bring your presentation up.
Thanks, Jen.
Ah, there we go. Okay. And I'm going to jump on the other computer and monitor chats. We're going to hold all questions for both Chris and Holger until the end of the two presentations. And I would ask that those viewing somewhere during the presentation, just send a chat saying how many people are viewing with you. We keep track of those things. Right now at UNH, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We've got 12 people sitting here in the room at UNH so far. So with that, Chris, I'm going to let you take this away.
Thanks, Jen. I'm here at JASCO in Halifax, Nova Scotia with 7 others for a total of 8 of us participating in the seminar today. I'm a project engineer at JASCO. My background's in electrical engineering and signal processing, and I've been involved with a lot of JASCO's measurements and field studies in marine acoustics for the last 10 years. So today I'm going to talk about acoustic technology for making underwater measurements, and the outline of the presentation will cover background motivations for doing measurements in underwater. I want to talk a little bit about understanding requirements for making underwater measurements. Then I'll do a little bit of an overview of technologies and approaches, talk about a few considerations on making good measurements, and finally I'll end up with some examples of current technology platforms that are out there. We have to first ask ourselves, what are you trying to characterize when you're doing an underwater acoustic study? And a lot of times it's biophony, presence, absence of mammals or fish, or behavior of animals or migratory pathways. A lot of studies involve anthropogenic noise, shipping or oil and gas surveys, or pile driving for piers or bridge construction, sonars, and other things. You probably, maybe the three of those pictures might be obvious, but the bottom right one may not be completely obvious what that is. If you haven't seen it before, that's a seismic survey vessel that's used for geophysical surveys for oil and gas. And the additional wakes you see behind the vessel's in the bottom of the picture. Those additional wakes, those would be the air gun sources being towed behind the vessel. They're quite loud sources, and they sometimes need to be measured. And then geophony, meaning natural sounds, and the natural sounds we might study underwater include ice noise, wind and wave environmental noise, or rain even, and geological activity. It's not really my area of expertise, but certainly a lot of acoustics are applied to those purposes. So the first thing I think that you need to do when looking at making an underwater measurement is understand your requirements. What do you need to capture? What's your sample configuration? What frequency range are you interested in? What time coverage do you need? Do you need to record a short period of time or a long period of time? What amount of space do you need to cover, physical space and area? And sometimes not first on our minds would be dynamic range. What's the loudest sound you need to capture and the quietest sound? And then factoring into all of these would be cost. Frequency range can go from single-digit hertz all the way up to hundreds of kilohertz, or even megahertz if you're talking about some man-made sounds. But low-frequency sounds would generally be tens of hertz to hundreds of hertz, and that would be cetaceans, low-frequency vocalizations of mammals, shipping noise, or actually I mentioned geophysical surveys, air guns that have a lot of energy. In fact, most impulsive sources like pile driving and air guns would have a lot of energy below 100 hertz, and still significant energy up to hundreds of hertz. Shipping noise is a major contributor to sound in the ocean, and shipping noise has mean energy below 500 hertz, but significant energy up to tens of kilohertz. And there's a whole other raft of anthropogenic sources you can talk about that would be anywhere from hundreds of hertz to hundreds of kilohertz, whether you're talking about echo sounders or side scan sonars or naval sonars or lots of other things. And then topping out the biological spectrum, in the middle there'll also be fish, mammal vocalizations in the hundreds or tens of kilohertz or tens of kilohertz. And then you get up to hundreds of kilohertz, like 120, 150, 180 maybe kilohertz would be your highest biological sounds, odontocetes and porpoise. Okay, thinking about requirements still, how long do you need to record? Is it an hour? Is it a day? Is it a month? A year? Those factors will impact your technology choice, your power requirements, batteries maybe if it's an autonomous system. It'll impact your sample rate, your duty cycle, and all of that will feed into logistics. Logistics meaning it's like a catch-all term, meaning ship time or shipping costs or manpower, labor. Space. You can use acoustics to listen to a very specific source nearby, and you might just take a hydrophone on a cable and put it over the side of a ship, or put it off a wharf, or in the case of this picture here, a lead in ice. The larger picture on the bottom is a jack-up rig installing a sheet pile platform, I believe, for an oil and gas installation on the right here. The wind farm on the left is sort of coincidental, but the foundations for those turbines would also have been pile-driven tubes, probably. All of those things create noise in the construction phase and are often measured with acoustics for the impacts on the environment. But then you can go up from there, and you can have studies that cover a whole sea or a continental shelf. These are two that JASCO have done, one off Alaska and one off the east coast of Canada, where we've put dozens of recorders out over a whole sea to study migratory pathways of mammals or broad scale statistics on environmental noise. And you can go farther up from there, and NOAA has the Noise Reference Station Network, which covers the EEZ of the US, including everywhere from the Arctic to Hawaii to the Atlantic and the Caribbean. And finally, you can have global scale studies or systems, and the Comprehensive Test Ban Treaty Organization is an example of that, with 11 hydroacoustic stations around the world intended for detecting nuclear explosions, but you can also get a lot of science out of that. They've told me about stations in Norway picking up oil and gas surveys off the south coast of South America and Argentina. So acoustics is a powerful tool for covering a large amount of area. Again, dynamic range, maybe not always the first thought, but it is an important consideration. So on the top left and bottom right, we have two anthropogenic sources, and the top left is a large impact hammer for driving piles for a bridge construction project. Again, that oil and gas survey on the bottom right, those two are really, really high level sources. So the loudest sound you need to capture there is quite loud. So you might need a very insensitive sensor. However, if the only thing you need to capture is that source, you might only need that one insensitive sensor. Likewise, if you're trying to capture biological sounds over a wide area, you might want a very sensitive sensor. But your dynamic range may still not be super large. The challenge comes when you try to capture all those things. If you want to get the background ambient noise, the soundscape, the biological sounds, and a very close by high level sound source, you might even need to have multiple sensors, one insensitive and one very sensitive, to capture the full dynamic range. So let's talk a little bit about technologies and approaches. And you can categorize or group these in a number of different ways, and there's no one perfect categorization. But for purpose of discussion, I've tried to divide things into fixed versus mobile and autonomous versus telemetred. And a fixed autonomous system might be, like shown on left here, a floating mooring, a subsea mooring with a standalone recorder. You might have mobile systems like a recorder hung from a ship that might still be autonomous and recording internally, and then you retrieve it and you analyze the data afterwards. You might have a fixed system with a buoy, a surface buoy, and a satellite link, so that might be sending back real-time results. Or you might have a cable to shore from a bottom installation, and those would be fixed telemetred systems. And then you could have both mobile autonomous and mobile telemetred systems like drifting buoys or gliders. And I'll talk a little bit about some of those now. One type of technology that you can use for acoustic measurements would be a cabled observatory. And I would call that a fixed telemetred system. There's several major examples of this, but the one I'm showing here is the Venus network off the coast of British Columbia, Canada. And Project Echo is a part of that observatory where a JASCO recorder is plugged in and streaming data to shore in real time. That is one of the advantages of a fixed telemetred cabled system. You have the data is coming back to shore right away. It's publicly available on the web with like a very short time delay. It has potential for really high data quality because you're not limited by power constraints, say, in an autonomous system. It's, you're cable to shore, you're plugged in. Downsides, that cable is very expensive, and the installation of the cable is expensive, and the maintenance of the system is expensive. So the cost of the system is probably pretty proportional to the distance from shore. And that also limits your location choices. So the applications of cabled observatories might be near shore, studies of long-term shipping noise, or maybe even specific marine mammal habitats. That's just some examples, it's not a comprehensive list. Another type of a fixed telemetry system might be a bottom-mounted buoy with a surface expression, and here's a spar buoy. It doesn't have to be a spar buoy, it could be other types of buoys. This type of system has the same real-time advantage. You get results back right away, but it's cheaper because you don't have that expensive cable to shore. But that satellite link is probably using iridium. Another example, so this one is a JASCO one, but there's Cornell did a installation of buoys in this sort of approach off of Boston Harbor, I believe. And it's less complex to install than the observatory, but it's still fairly complicated compared to some of the other examples I'll go through in a second. And the other thing I was going to say about the data rate, the disadvantage of data rate, is that satellite link is probably going through iridium, which is a tiny, tiny straw. It's a very, very narrow pipe, so you can't send back the raw acoustic data. You're sending back some kind of process results, SPL levels, or maybe detections or something like that. So the applications can include locations farther from shore than you can do with a cable observatory. You might be doing that for studying shipping or for mammals or biophony or even ambient noise. Fixed autonomous systems, like a moored data logger or acoustic recorder, this type of approach is a very common approach to acoustic measurements underwater. It has the potential for really high data quality if done right. You know, there's a lot of variability in that, but it can be very, very high quality data, and it can be done very reliably. Maybe medium cost, not as expensive as those cabled observatories, but maybe not as cheap as some other things. Disadvantages, you're measuring one location, and that location is usually fixed, and it's not real time. You're going to get back a huge chunk of data, a day or a week or a month or a year of data is going to come back all at once, and you have to analyze that after the fact. So it's not good for real-time applications where you need to detect an event and then take an action. But it's great for studying remote areas of the ocean, because you can do this in the deep water of the main ocean basins. You can do it in the Arctic. And it's also useful for spot measurements of industrial activity. If you need to know precisely where your measurement device is, a fixed autonomous recorder is sometimes a good option. I would consider that over-the-side measurements, like take a hydrophone and put it over the side of a ship, is maybe a little bit of a case to itself, but you could probably consider it a mobile telemetered system, and potentially could be really low cost. The system you should see on the left there is probably an order of magnitude cheaper than any of the ones I've shown so far. Not necessarily low cost. If you wanted to do a measurement further offshore from a bigger vessel, then your ship time costs might drive your total project cost, and that's what I meant by logistics earlier. And so that's one of the downsides, time. You only are making that measurement for the time that your ship is, or your boat is where you want it to be. But it's real time. You put the hydrophone in the water, and you listen or you record, and you're getting data now, and you can detect things now, and you can take action now. So that could be used for recording mammal vocalizations, whale calls, or other things like that. Again, or spot measurements of industrial activity. Lots of other things as well. Oh, right. The picture on the right is actually a towed array, and that's widely used in military applications, and it can have applications in science as well. That nudges the cost a little bit up, though, as opposed to the easy, simple one hydrophone over the side kind of measurement. Finally, I'm going to quickly cover some mobile telemetered options that don't have that time limitation of a person holding a hydrophone over the side of a ship. So drifters and gliders it started to be developed in the last decade or two, and in recent years people have started to put acoustics on them. That gives you the potential to cover wide areas over long periods of time at lower cost, of course, is implied there. Downsides, it's still a challenge to get really good quality data from a moving platform. And the data rate, again, like the fixed buoy with the satellite link over Iridium, profiling float or a glider is also using that same kind of satellite network. And so it's, again, a very narrow pipe, a very small straw to get data back. So you're talking about process results, sound levels, or detection events, which also has implications for the complexity of the instrument. You have to have a more powerful processor to do something with the raw acoustics before you can send it out over that satellite link. So quickly, some considerations for doing good measurements. There's a lot, and I'm only going to touch on a few really quickly, but a big one is the environment. And there's lots of things, but current bottom type bathymetry are some of the main ones. For some types of studies, you really want to be aware of calibration of your sensors and your transducers. Data quality, kind of a catch-all term here for thinking about what you need in terms of frequency response. How important is absolute frequency response for your type of measurement? What do you do about sensor mounting and mooring performance? That one really applies to autonomous fixed measurements like a moored recorder, although it might have similar parallels in some of the other platform types. Finally, think about data volume. Acoustics generates a lot of data, and that trend is only going up. Very quickly, water flowing over a hydrophone or flowing over a transducer or around a measurement platform has an effect on acoustics at almost any speed. The pictures on the left are in a test tank, and at 80 centimeters a second, this middle picture, obviously the current is pulling the instrument way down, but aside from moving it from its desired location, you've also got the flow over the sensor itself causing a lot of noise. The thing you don't see in these pictures, these still pictures, is that not only is the instrument moved off of the vertical position, which doesn't seem like such a big deal, it's actually sort of waving in the breeze. It's oscillating back and forth continuously at a hertz or two. It's just cycling back and forth. And that continual swishing of your sensor through the water is affecting the data quality all the time. Even at 20 centimeters a second, this effect is happening. It happens at 10 centimeters a second, 5 centimeters a second. It's a pervasive problem. If you get above a knot or two of current, up to above about a meter per second, you might need to take special consideration to do good quality measurements underwater. If you get a lot above a knot or two, it might be extreme considerations. And the picture on the right is a flow shield for extremely high currents. It's also very heavy, which affects the ship that can deploy it, which affects your costs. Calibration can be critical for characterizing, well, it is critical for characterizing absolute source levels. If you're trying to measure how loud is an oil and gas survey or how loud is a container ship, you really have to be confident in your calibration. And our experience at JASCO is that it's taken a lot of experience, a lot of time, many calibrations with many sensors for us to fully understand some of the subtleties and fully work out some of the kinks in our hardware and our procedures and our software. Now, if you're trying to characterize humpback songs, perhaps your absolute sound pressure levels are not as important. So all this will affect your equipment selection. Some sensors and some recording platforms are better suited to good calibrations, and others are less suited and maybe less expensive. And like I said, procedures, experience, and training are important for getting good calibrated data. Mooring design is a broad topic, and I don't have time to get into all the details, but sensor location is one I briefly wanted to mention. I don't have a picture of the actual sensor involved, but these two plots, I'll try to explain them very quickly. They're the same plot from the same recorder at the same time, the same place. The only difference between these two plots is the hydrophone is about a meter. One hydrophone is about a meter away from the other. So these were both recorded from two hydrophones at the same time, placed with the same recorder. This is a percentile plot. So on the x-axis is frequency, on the y-axis is power spectral density, and the colored lines are percentile, like the percentage of the time that the power spectral density exceeds a certain level. On the left, It's a fairly smooth curve that it's pretty representative of the ambient noise. And the right is a hydrophone that is immediately adjacent to a instrument housing. I was wrong when I said that these are both the same recorder. Sorry, they are the same place and same time. The left one is an AMR with the hydrophone removed from the recorder. It's out on its own in the water. The right is another data logger. I'm not going to try to criticize another manufacturer, but obviously if you're recording marine mammal vocalizations, the difference may not matter. If you're trying to characterize the sound signature of a man-made noise source and you're reporting on that, the sensor position for the instrument on the right is obviously not giving you an accurate picture of the real noise in the environment. So sensor location is really important, and there's a number of things about study design and mooring design and hardware that's covered in this hardware standard on the ADION project. The links are at the bottom. One other thing about mooring design, eliminating noise sources is a challenge, and I've already talked a bit about mooring motion. I'm not sure if the animation is coming up very well over the web, but the animation on the top right is showing the vortex eddies that are being shed off of a cylinder fixed in a fluid flow. And that's sort of a generic representation. The eddies coming off of the device, whether it's a recorder or a mooring wire or a float, the eddies aren't really the issue. The issue is the asymmetry of that eddy production creates forces on the object itself, which is what makes something move. So if there's a current flowing over a wire or a float or a recorder, there's eddies being formed, and that recorder is moving perpendicular to the current flow. So everything moves in the water, especially if it's floating or whatever. And that creates noise. I've already talked about the flow noise of the water over the sensor itself, but there's also mechanical noise. You might have strum in your ropes or your wires. You might have loose fittings clinking. You might have shackles making noise. So eliminating noise sources is quite a challenge. That plot on the bottom left is another percentile plot, frequency versus power spectral density. Above about 100 hertz, the percentile levels are pretty tight together, meaning the frequency characteristic of the sound varies pretty much linearly with amplitude. So sometimes it's loud and sometimes it's quiet, but the overall shape of the frequencies of the ambient noise field are fairly similar. The spread below 100 hertz is primarily not real. It doesn't mean that, oh, sometimes it gets really loud and it's all primarily below 100 hertz. No, this recorder was on a mooring that moved a lot, and when it started moving a little bit, you got flow noise below 100 hertz, and that's not real. So careful consideration in mooring design is a challenge. Finally, quantity of data. We're already doing field trials on the next generation of JASCO recorders, and I assume that other technologies are in the same process, in the same ballpark. 10 to 20 terabytes capacity in one single recorder, which means months or years of continuous recording at high sample rates and multiple channels. That means you're not dealing with a pile of hard drives on your desk anymore. You're dealing with data centers and server rooms, and so infrastructure and automated tools are going to become more and more important. All right, let's wrap it up with a few examples of the technologies that you might come across, and we'll just flash these up fairly quickly and then hand it off to Holger. So streaming recorders, that's what we said earlier, might be a fixed telemetered system. JASCO has AMRs that do this, and our new system's called the Observer. Ocean Sonic's IC Listen is also an example of this type. I think there's probably a couple others that I missed. Autonomous recorders, you probably are aware there's a wide range of data loggers or autonomous recorders. JASCO's G3 and G4 systems are pictured here, and then there's a number of others. And if we had more time, we could play a fun game of who can identify correctly all the different data loggers in this picture. And then there's a few that are not commercially available, but they are also in the same category of data logging acoustic recorders. Cornell has the Maru, Scripps has a Harp, Hui has the shrew, and again, I'm sure there's a few others I've missed. Gliders. I said earlier, these are starting to be adapted for acoustics, and I know there's a few research groups at universities doing this, and JASCO's involved with a few others. Teledyne Web has the Slocum, which see a lot of Kongsberg Sea Gliders in the bottom middle. Top right, the Alcimar Sea Explorer. Those are just three of the better known ones. And then there's Liquid Robotics Wave Glider is another platform that has been investigated for acoustics. Profiling floats. These are well established in the Argos network for physical oceanography, for conductivity, temperature, pressure, lots of other physical oceanographic measurement. And now these manufacturers are starting to adapt them to biogeochemical and acoustics. And so JASCO has been involved with putting acoustics on a couple of profiling floats. And again, I'm sure there's other people involved in that. And that's it. That's my overview of marine acoustic technology. So I'll hand it off to Jen and Holger.
Yeah, thank you, Chris. We are going to move on. You stop good. You stop sharing. Holger can share, and we're going to hold questions until the end. Let's see. Hopefully Holger will share his screen, and we should be on our way.
Working on it.
There we go. Perfect. You're live.
Okay. Well, thanks a lot to Christopher for providing this really nice introduction for acoustic technology for marine applications, and a lot of design consideration for experiments and technology obviously apply for the acoustics world in the terrestrial domain as well, so I won't go into too much detail there again. What I want to outline first is to talk a little bit about fundamental differences between terrestrial and marine acoustic research. Christopher just said, in the marine domain, a lot of questions we're dealing with are the who and where, so still basic applied research questions where we use this really sophisticated equipment as drifters, gliders, and cabled array, and all that sort of thing. And a lot of that is just driven by funding which is available. So a lot of the work is being funded by the Navy or by the industry or regulatory agencies. And it's about, monitoring and mitigating impacts of whatever activity there might take place. In comparison to terrestrial world, is much more on the basic research side of things. There is no Navy or not these large industry or other funding agencies which do currently this really large scale monitoring. A lot of funding from NSF there to look in, for example, communication networks in animals and that sort of thing. So monitoring on landscape scale is still in its infancy, really, in the terrestrial world. And probably the large scale which has been happened in that domain is surveys for bats, especially here in the eastern part of the US, where we have to deal with the white nose syndrome, which is wiping out lots of bat species. Generally, I'd say there is very little interactions between the two community, which is really a bummer. So we as a whole community could and should do a better job to build bridges between the two subfields, because I think we can learn a lot from each other. And then if we're looking at the data handling and also the analysis, there are a lot of commonality where, if we put our heads together, some really good things could happen, I think. Talking a little bit about the technology, and people have been doing recordings with parabolas or shotgun mics, as you can see here, and I listed here a few URLs where you can get more details on those kinds of recording equipment. I won't talk about it. But this is what has been used for many, many decades to record animals in the terrestrial environment. The nice thing about that is that you typically can combine those with concurrent visual observations. There are literally thousands of applications just in the world using those kinds of recordings to describe, acoustic phenomena in in bird species. So a lot has been done there. But on the larger scale, autonomous monitoring side of things, that is still something we're working on. And
Holger, I'm going to interrupt you for a second. Your audio is cutting in and out. I don't know if it's because you're standing differently, but I just wanted to let you know that we're having a hard time hearing you a little bit.
all right, is that better?
Yeah, we'll see. I'll let you know if it's not.
All right, thank you. Sorry for that. So over the last, I will try to speak a little bit louder too. So over the last couple of years, you know, there were companies who started to supply commercial.
Ziploc bag.
Sorry?
Oh, sorry.
So over the last couple of years, there have been several companies which are now producing this terrestrial autonomous recorder. And you can see here on the, I'm not sure if you can see my little pointer here, but on the left you have the audio MOS, which was developed by a research group in the UK. In the center there's a Frontier Labs recorder developed by Frontier Labs, a company in Australia. Then in the upper right is the Swift recorder. That's the one we're developing and using. And then on the lower right, there is the song meter, which is also being widely used to do bird and bat research. So there have been, you know, it's not as diverse the kind of archival recorders you see in the marine domain, but there's certainly now, you know, these companies popping up, providing these kinds of instrumentations for doing research. And I wanted to briefly show you two examples of large-scale monitoring efforts we're involved in. The first one here is about the California spotted owls. As you might know, there are three spotted owl subspecies. The first one is the northern spotted owl, which occurs in the coastal areas of Washington and Oregon, and that population is doing really poorly. They have problems with logging of old growth forest, and then from the east, the barred owls are moving in and out competing those guys. So the northern spotted owl is doing very poorly. In California and the Sierra Nevadas, there is the California spotted owl, and there is concern now that as the barred owls are expanding further south, that they're moving into spotted owl, California spotted owl territory, and also displacing those animals. So we have currently 100, and we'll have this spring 200 recorders out there north of Lake Tahoe, in the Lassen National Forest and the Plumas National Forest. And you can see here on the right, I won't go into too much detail, where we move the recorders around and monitor for those two owl species. And that's is a project which is done in collaboration with the University of Wisconsin and San Jose State University, and funded by the Forest Service. Another one which we're doing here in the lab, and this is a great example. This is a picture of the Central African rainforest, and you know, I compare it to the ocean because that's what it really is. It's a green ocean which is very inaccessible, and monitoring the movements or the presence of animals is almost as challenging as doing it in the ocean. And so one area we're working a lot is in the Congo, Cameroon, Central African Republic area. You can see it in the upper right here in this red box. And there is the Nuambuldoki National Park, which is adjacent to logging concessions. And there is a big problem there with human-animal conflict. Because they're producing these, putting logging roads in place, there's also an increase of poaching activity. It makes it easier for poachers to get in these inaccessible areas and hunt forest elephants. So we're currently operating an array for the next probably 3 to 4 years in this area of at least 80 recorders, where we try to assess movement patterns of forest elephants in this area, and also do some density estimation to monitor this population more closely. And this is done in collaboration with the Wildlife Conservation Society. Real-time is being done in the terrestrial world as well. There we have some advantages because Often we can use cell phone networks, or we have direct access to Wi-Fi, so our bandwidth is typically a little bit better than what it is on the ocean, where you have to use, as Christopher said, iridium mostly. So this is a system we have been using to monitor migrating birds. And how it works, you have a flock of birds you can see here flapping in the upper right, and they produce these night flight calls, which sound like this. I hope you can hear this. So these are very short notes, typically a few kilohertz in frequency, and they're presumed to be used to for group cohesion during the night flight. So we have these recorders out in the field which are listening in real time for those night flight calls. And if the unit detects something which it believes is a night flight call, then it's being transmitted. And we typically use a cell phone network to do that. So sending actual sound snippets is not a problem for us. And then here on the server, we have a more complicated classifier running, which then classifies the night flight call to a species level. Though in this case, that was a Swainson's thrush. And here you can see what the unit looks like. So inside, most of the electronics are actually based on a Raspberry Pi. The most expensive part which is in there is probably the cell phone modem. So that's another advantage we have. We don't need titanium pressure housings or things like that. It's everything is much, much cheaper once you start to work above sea level. And as an output, what it looks like, you can see here on this map. This was a pilot study we did. I hope you can see these green dots, which are active listening station. And as detections are coming in on the right-hand side, you can see the night flight calls. They're showing up from one of the stations, and then it's automatically generating bar graphs, etc., which we can then further process. So where do we use this? One kind of exciting area of research in the terrestrial world is what we call dark ecology. What you can see here is animation of one night of radar data across the entire continental US. So there are about 50 of these radar stations distributed over the US, primarily to track weather. You can see this front here moving from the west to the east, so that's what they're really being used for. But Amazon last year decided to host all the historical and all the data moving forward from this data, and gives researchers free access to process its data for other information they're interested in. And if you pay attention to it, and you can see up on the top right, there is a local time running. Once the sun goes down, you see these plumes of radar signals coming up. And what that is you can see this is in September, so that's fall migration. And these are insects as well as birds, starting to move. And a lot of the research which is currently being done on this radar data is to extract information on bird movement patterns, and also figure out how many birds migrate through the US, make it into the breeding grounds, and then come back. The problem with the radar data is you cannot identify species. It's basically species agnostic. You can get information sometimes on size of birds, but it's really not a tool to get down to species levels. And by pairing that with acoustics, we can basically provide complementary data which allows those guys to do better assessments of individual species migration. Another one is the 9/11 tribute in lights. You're probably familiar with that. Every year they turn on these monuments with these massive light columns, and all these spectacles you can see there in the pictures are actually birds. So obviously this monument is being turned on at 9/11, which is often a time period during fall migration when a lot of birds migrate. And what it sounds like, I hope you can hear it. These are tens of thousands of night flight calls which are emitted by migrating birds, which are basically caught in these two light beams. So they're circling those columns, and often what happens, they bump into each other or die of exhaustion. And from the beginning on, the organizer of this event had an interest to minimize impacts of bird species. What you can see here is a timeline. So it typically turns on at 8 in the evening and goes till 6 in the morning. That's when the monument is active. And these cycles here are actually cycles in calling activity. And these are correlated with lights off on period. So we have acoustic sensors there which measure the calling intensity. And at some point we tell them to turn the lights off for a brief period of time so the birds can escape. So you can see once the light is turned off, the birds disappear fairly quickly and continue to migrate. But also once you turn the light on, it takes only very brief period of time, and then you have a lot of birds again caught in the beam. Another interest is definitely poaching. We get a lot of, we're being approached from a lot of people around the world actually who are dealing with this sort of issue. This is one example. This is a study we conducted actually in Korob National Park here in Central Africa. You can see it's at the border between Nigeria and Cameroon. And there is, in this case, not poaching going on for forest elephants, primarily bushmeat, as you can see here on the pictures on the right. And there was a bunch of recorders in this area deployed. It was a 2-year continuous recording effort where the gunshot activity was monitored because the rangers there have very limited financial support, and they wanted to focus their effort in certain areas or certain times of the week when it makes the most sense for them. And this actually showed that most of the gun activity is going on here in the northwest, closer to the border to Nigeria. And what you also can see, interestingly enough, is that most of the shots are going off during midweek, and we believe that's related to the fact that end of the week is typically the market day when the meat is being sold. So they hunt primarily during the midweek and then sell at end of the week. And that is really valuable information for those rangers to try and make an impact and reduce the poaching effort in this national park. But of course they say, well, it would be really even better if we get some real-time information on when gunshots are happening. So that there is certainly in the terrestrial domain a large need for, better real-time monitoring systems. A few words about metadata. Metadata is really important. The people working in the marine world are very aware of that. From what I can tell in the terrestrial world, it's the Wild West, really. Everyone stores data differently. A lot of people don't store the necessary metadata, which makes the data useful for future studies, maybe conducted by someone else. So that is certainly something which needs to be improved. There's so many people collecting data, but if the metadata is not being collected and not accurately available, then that's a big problem. And there's one effort I would like to point out, which is a standards working group, an Acoustical Society of America standards working group, which is led by Marie Roche, and she tries to develop these standards for metadata for both the marine as well as the terrestrial domain. I don't think in the marine world it's that big of a problem anymore. We have done a good job of making sure that we're collecting that data, but there's certainly a need for better standards in terrestrial world. The last few minutes I have, I would like to talk about a specific project which we have going on here in Ithaca, New York, which we call SWAMS, the Sapsucker Woods Acoustic Monitoring Project. And what we do, so you can see here, this is where I'm sitting right now at the Cornell Lab of Ornithology, and we have the sanctuary which is about 1 square kilometer in size surrounding our lab. And about a year ago, we deployed this array of 30 acoustic recorders, which record continuously at 48 kilohertz and 16-bit resolution in this case. And every month, someone is going out and maintaining and bringing back, changing batteries and bringing back the data. So we have now completed 1 year of data collection, and we'll continue to collect data in this area. And the questions we're trying to answer is, a lot of people in the terrestrial world try to figure out, can we do a bioacoustic splits, go into an area, record for a certain period of time, and then figure out what the biodiversity in an area looks like, and maybe what that can tell us about the ecosystem health in that area. Now, for our purpose, birds are a good indicator for biodiversity, so our research obviously focuses on birds. And one of the basic questions we try to answer is, what, even in this small kind of setup, what is the spatial variability? So if we look at, for example, the southeasternmost or the northwesternmost recorder, are those producing the same results if you look at them independently? So we want to provide people with information, what would be a good spatial setup to get the information you need. And the same is true for the temporal variability. So for how long do you have to record to get the information you're after? And obviously we're collecting a lot of data right now, and not a lot of people, at least not in the terrestrial world, will be able to deal with that amount. So we're trying to produce this nicely annotated data set, which we also want to make available to others who are interested in it and want to work with it, to figure out some of these really basic monitoring questions, which have been a lot answered already in the marine world. And the nice thing about being at the lab of O is that we can also collect a lot of ground truth data. So we have these 11 caching sites where people go out and do the traditional point counts, and then report those back to us. And since, it's kind of a mecca for birders, we get a lot of good and a lot of information about visual counts in that area, which is very helpful to us. So they submit these checklists, which tell us where and when certain species were seen, and then we get these bar graphs you can see here, which illustrate how many birds and which species occurred at various areas of Sapsuga's Wood Sanctuary. So obviously those recordings are fairly complex. Not right now, because most of the species are not here, but if we're getting into May and all the migrants are coming in, we're dealing with a lot of different species and vocalizations from a different species. So, that is a significant difference, I think, compared to the marine world. There are only about 119 species of marine mammals in the world, but there are 10,000 species of birds. Now, we don't have that many in upstate New York. It's a few hundred, but still, it's a lot of different signals you get, and teasing all those apart is not a trivial exercise, especially considering that a lot of them call at the same time during dawn chorus. And I think because of that, a lot of people in the terrestrial domain, and I won't only spend a little bit of time on that, are looking into biodiversity indices. I think that because the detection classification have become overwhelming and there's not that kind of expertise there, people try to apply these biodiversity indices, as you can see here on the left-hand side, where they use 3 different indices to generate these false color spectrogram. And I'm not a big fan of them personally. I think it's a shortcut, and eventually we'll have to deal with the detection classification stuff. There are over 30 indices now out there, and it's often not clear which one is the best for your question. They're hard to quantify, and there's also a lot of questions about how representative they actually are. Another question, there was recently a really interesting paper in Science about functional biodiversity, where people ask, biodiversity is interesting, but you really need to look into the function the various species in your ecosystem have. if you have one species in there which has a very specific task in this ecosystem, and that one species disappears, that can have a really detrimental impact on the environment. And so looking at species is important. And for the most part, I'm not sure why people don't do that in the terrestrial domain, but from a long-term spectral average plot, what you can see here, which is about 10 days or so, which a postdoc of mine collected in Borneo, you can get a lot of the pattern. They're trying to tease out these biodiversity indices plots as well, like rain, here the bird chorus, and then the insect activity. So over the last few years, people in the terrestrial world have started to look into deep learning. And I don't have time to talk a lot about it, but I want to, if you look at this little graph here on the upper right, that's really an interesting one, which basically tells you the performance of, say, a classifier depending on the amount of data you have. You can see as at lower amounts of data, the older as a traditional machine learning algorithms and deep learning perform fairly similar. But you get at a point, at some point, where you have so much data where deep learning can really make a difference. And that, I guess, is one of the advantages we have in the terrestrial domain, especially if you work with birds. There is a lot of data available you can use to train these kinds of systems. And we have been working on that for a year now, and we're focusing on 150 species which occur in the Sapsucker Woods area and have made really good progress. So the nice thing about that is you don't do a traditional feature extraction and classification anymore. The deep learning actually figures the features out from whatever input, in our case, it's cleaned up spectrograms we provide to them. There are modifications to that. You don't have to use deep learning to do the actual classification. So some people basically cut off the last layer, the classification layer, and only use the deep learning for the feature extraction, and then pull these features into, for example, a support vector machine. And there is now an ONR project going on, which is Marie Roche is a PI on that project, where she is also trying to apply some of these deep learning algorithms to solve some of the marine mammal class detection and classification issues. So I'm excited to see that being used on the in the marine world as well. And this is what our prototype currently looks like. This is a recording I made yesterday, so you can see there's not a lot of stuff going on. There are some blue jays mobbing and calling there, and tufted titmouse. So there is a prediction window you can see in the beginning where we parse a spectrogram continuously into the neural net, and then it makes a prediction of what its things is occurring in this during this time period. And then on the lower right here, you can see how many calls were detected and classified over the last 60 minutes. And down here, you can see this is a probability from 0 to 1 as produced by the system. And then you can see how the species are bouncing around. So I think this is a nice start. We have still a lot of work to do on that one. We're currently annotating a lot of the data we collected over the last year in Sapsucker Woods to also use multi-species labeled data for training to improve our accuracy or precision when we work on the more complex soundscape data. And quickly, a summary. I think really it is important to bring researchers from both fields together. I think there's a lot of which each world would gain, and Jen's effort to some degree aims to do that. So I'm very pleased about that. Landscape scale monitoring is really not that common yet, but it's gaining traction. It will be important to make sure that the data which is being collected is collected with, again, the metadata, so it's also useful in the future. There's a need for a more effective real-time solution, so I hope people will start working on that and producing also cheaper solutions than we have right now. As Christopher already said, the challenges ahead will definitely lie in the data handling and the analysis. The data collection, we can collect a lot of data, but we're still lagging, a lot of analysis power to get the information out of the data we need to. And I'm convinced that deep learning, from what I have seen so far, will change the way we're analyzing the data. So in 10 years from now, a lot of people will be using this kind of technology and algorithms. And that's it. Thank you.
All right, thank you guys. We're going to give you virtual applause since you can't hear it from everybody. And I want to assure both speakers that your animations and your sounds played through here in UNH just fine. And at this point, if anyone has any questions, let's go ahead and ask. I know we're over time a little bit, but if you have questions, let's do what we can to ask them.
You want to put up the chat on the screen?
Oops. Let's see, I can do that. I'm not seeing any questions coming in over the net right now. I see thank yous and claps, so we do have virtual applause here. Anybody from UNH in the room have any questions? There's one question.
I have two.
Go ahead.
So the site where you had 200 autonomous recorders, I know sort of how much under a marine acoustic recorder, autonomous recorder would cost. What was the price of those 200 recorders that you could afford to do that?
Am I muted?
What was that? We can't hear you.
Can you hear me now?
Yes.
Okay, so the recorder typically costs, these ones which are being used, $250.
Okay. That's sort of an order of magnitude.
There's
probably two orders of magnitude. Yeah,
maybe 2 orders of magnitude. Yeah.
There's a question for Chris online. What does Chris think about the opportunities for acoustic modem networked instruments in the future?
It's not really my area of expertise, but lots of people are interested in using acoustics for communication. The challenges you have with telemetry through acoustics underwater are somewhat similar to the satellite telemetry in that you have a very narrow pipe. So you're talking about passing processed data, not raw data, and that means you have to have more smarts at the sensor in order to do the processing. And then the additional challenge is your acoustics comms then stomping on the thing you're trying to measure sometimes. You can maybe put the modems out of the frequency range of the thing you're trying to measure, but it's quite challenging, and power is really one of the big factors because you're often talking about an autonomous system that's away from like land-based power. So you're trying to last for weeks, months, years on a battery pack. And so you're very, very power constrained.
Awesome. And just for people who don't have a big screen in front of them, there was a question, do terrestrial applications use acoustic arrays to track birds like people track marine mammals? Is there any way to use this on land? Holger did answer online. No, they actually don't. And yes, there is a use on land. Let's see, someone from UMass wrote in, Doug Jones at UIUC did some work on arrays for bird tracking. So if people are interested in that, that's a good tip on where to go look for some literature.
Wasn't there a rooftop array throughout New York City tracking migratory birds a few years ago?
Carrie asked, wasn't there a rooftop array in New York City tracking migratory birds? And that might be just detecting them, not tracking individual birds? Maybe?
No, I mean, you can do that with a cabled array in that case. Yes, that's true. The problem is with and that's a disadvantage of these low-cost recorders, you don't hear a bird over hundreds of meters. So it's typically a few hundred meters. So you need to have a tight array. And getting the timing right on these is typically nothing those recorders do. Then you need to hook up a GPS or provide some external clock or accurate clock to keep the timing really synchronous. You can do the localization work. And the recorders which are currently out there, the basic ones typically can't do that. So there are some people who build specialized equipment for shorter term experiments where they look in counter calling or something like that. But there's a lot of work which could be done doing tracking of birds or whatever you might be interested in.
I think you just answered the second question that came in. What are the typical ranges for acoustic tracking of birds or atomic clock times? Do either of you have any input on atomic clocks or any additional information on typical ranges for acoustic tracking of birds? That'll be our last question since we're over.
Well, I think, JASCO is using the CSAC atomic clocks, but I'm not sure what they run for these days. I think the chip scale one costs several $1,000s. So people doing the terrestrial work can't afford those. And I would say a couple of 100 meters is probably our detection range for birds.
If you're in air and you have access to the sky, getting precision timing from GPS is like 3 orders of magnitude cheaper than atomic clocks. If you're underwater and you need precise time, atomic clocks are awesome. Yes, they are several $1,000s each, but if you're putting an array of instruments in the Arctic, your vessel is going to cost several $100,000 for the trip, so a few $1,000s on atomic clocks is not a deal breaker.
Yeah. All right, we're going to cut it off here since we're over time. I want to thank everybody for attending, and especially thank you to our two speakers. Your presentations came through just great. Thank you. We'll have that online for the public and people who missed it, hopefully within the week. All right. Thank you, everybody.
Bye.
Bye. I'm going to end the meeting, so I'll have to stop recording first.